Alright, so these are the notes for the intermolecular forces of attraction. Like this says, it's the governing rules to determine how one particle interacts with other particles. The really important part is to understand they go from weakest to strongest. There's three different types. It's the induced dipole, the dipole-dipole, and then the hydrogen bonds. I'm going to start with the dipole-dipole because that makes most sense. The dipole-dipole bonds, that's what happens when you have two polar molecules being attracted to one another. Those two polar molecules, they are polar because they have charges at either end. For example, this molecule methane, not methane, but dichloromethane. The dichloromethane molecule right here, okay, has a positive end which is this right here. Then it has a negative end of the molecule over on this side. The negative end is because of the chlorines, the more electronegative element. The positive end is due to the hydrogens, which are more electronegative. The attractive force between one molecule and another, represented by those little red dots, that is the intermolecular force of attraction. This molecule here is attracted to this molecule here because their opposite ends attract. That is what a dipole-dipole bond is. There's another type of dipole-dipole bond that's dependent upon being a really, really strong dipole-dipole bond, a super dipole-dipole bond. That occurs when you have hydrogen covalently bonded inside a molecule to either nitrogen, oxygen, or fluorine. When that happens, it creates a very polar bond and a very polar molecule. And that's what this shows here. The water molecules, they are strongly attracted to one another, and they create strong dipole-dipole called a hydrogen bond. Again, it's an intermolecular force of attraction that occurs when you have a very strong or a super dipole-dipole bond. The weakest intermolecular force of attraction is called an induced dipole, or it's created when you create a dipole. This happens in non-polar molecules, things like hydrogen, molecular nitrogen, or methane, CH4. Those are non-polar molecules. And because those are non-polar molecules, they have no attractive forces between them and other molecules. They have very, very weak or no intermolecular forces of attraction. However, if those molecules are forced together by very high pressure or very low temperature, or both, if they are forced to get close to one another, they create a dipole, and that dipole-dipole that is created or induced, that is called a London dispersion force, and that is the weakest intermolecular force of attraction. That is what holds nonpolar substances together when they become a liquid. Let's consider methane and methanol. Methane is a nonpolar molecule, whereas methanol is a polar molecule. This is because of the hydrogen bonding opportunity. The only difference between these two molecules is methanol has an oxygen atom in between the carbon and the hydrogen, whereas methane does not. That oxygen atom creates a very, very strong dipole. We end up with a very highly electronegative element in oxygen and a very low electronegative element in hydrogen, thereby creating a strong dipole moment. That strong dipole moment is what results in hydrogen bonding. That hydrogen bond makes that methanol molecule stick to other methanol molecules substantially. Because of that superpolarity in methanol, the boiling point difference between methane and methanol is substantial. Methane's boiling point is negative 161.5 degrees Celsius, whereas methanol's boiling point is 64.7 degrees Celsius. That is all attributed to that strong intermolecular force of methanol versus methane. Methanol has hydrogen bonding, whereas methane only has London dispersion forces. And because of that, there is a very weak intermolecular force in methane, a very strong intermolecular force in methanol. Methane molecules are not held together very strongly. Methanol molecules are held together strongly. Therefore, it takes more energy to separate the methanol molecules from one another. When we talk about hydrogen bonding, there are three compounds you must know, you must recognize, you must understand what those are. They are hydrogen fluoride, water, and ammonia. Those three will be mentioned on the Regents exam frequently. So let's take a look at this worksheet, InterMolecular Forces of Attraction worksheet. The first compound we have is nitrogen. The formula for nitrogen is N2. So when we do the Lewis structure, we have to talk about our have-needs. So we do our have-needs analysis. So each nitrogen has 5 valence electrons. Each nitrogen atom requires 3, or needs 3. So we have a total of 10 electrons to work with. We're only bonding with 6. That means we have 4 remaining left over that are unused. When we put 6 electrons between 2 nitrogens, we get this, and then we add our remaining extra 4 electrons for each atom. So those are 4, 2 on each, and we end up with a stable octet. Each nitrogen has a stable octet. We now need to consider the shape, and we have 2 things, so therefore it must be linear. A linear molecule of 2 elements of the exact same element is absolutely going to be nonpolar. And so the major intermolecular force of a nonpolar molecule is an induced dipole called a London dispersion force. Therefore, nitrogen, molecular nitrogen's major intermolecular force of attraction, is the London dispersion force. For the remaining molecules on this worksheet, I encourage you to take out this handout that I've given you. This shows you the group 14, 15, and 16 elements and compounds they make and the different shapes. Group 14 are going to make either a tetrahedral if they're attached to 4 different substances, 4 things. If a group 14 element is attached to 3, it's going to be trigonoplanar. And if a group 14 is attached to 2 things, it's going to be linear triatomic, which may or may not tell you the symmetry, but it tells you the shape. Similarly, group 15 and group 16 elements, 3 things, 2 things, 1 thing, or 2 things and 1 thing.